Welcome to lecture 8. We are studying electronic devices and circuits EDC. Today we will see numerically the difference between exact and approximate analysis, and we will see how different are the results produced by these two analysis techniques for a voltage divider bias BJT configuration. First, we'll solve this given circuit where we have these given values of R1, R2, RC and RE and beta 100 for exact analysis, and then we'll repeat the same calculations for approximate analysis, and then we will compare. First, let's solve this using exact analysis. As we know that while applying the exact analysis, we apply a voltage divider theorem where all this on the right of this dotted line is considered as a load and is removed, and then we calculate V Thevenin, which we have already done, R1 R2 over R1 plus R2 times VCC. Putting these values here, we get V Thevenin is equal to 2 volts. Similarly, R Thevenin is the parallel combination of R1 and R2, which comes out to be 3.55 kilo ohms while we put these R1 and R2 at 9K and 3.9K. The next is that we replace this hole with a resistor having value R Thevenin and a voltage source having value V Thevenin, and then we analyze, we write input and output loop equations, and while we write input and output loop equations, the values of IB and IC, IB we have already solved it in an earlier lecture. The input loop equation yields IB is V Thevenin. You can consult your old notes, VBE over R Thevenin plus beta times RE. It gives a value 8.38 microamperes. Since beta is 100, IC is 100 times 8.38 micro, yields 0.84 milli. In the output loop equation, we put the value of IC to find VCE. We have written the output loop equation in many of our previous lectures. Output loop equation yields VCE 12.34 volts. The same problem can be tackled using approximate analysis. Going back to the original circuit, we assume that this VB voltage is computed using voltage divider theorem here, and we also assume that IB is negligibly small compared to the current flowing through this R2 resistor. For that, we check whether we can apply this approximate analysis or not. To check, we test beta RE over 10. If R2 is less than beta RE over 10, we can apply approximate analysis because the current flowing into the base will be negligibly small compared to the I2. Since 3.9K is very small compared to 15K, we can safely apply approximate analysis. We apply approximate VB, this voltage drop is 0.7, so VE voltage would be the voltage of emitter terminal with respect to ground is VB minus 0.7, and IC, which is approximately equal to IE, can be written as VE over RE which turns out to be 0.867 milliamperes. And we can add output loop equation to find the value of VCE, which comes out to be 12.03 volts. Now we compare the two values of IC and VCE obtained using exact analysis and approximate analysis in a table. IC milliamperes, VCE in volts, using exact analysis, using approximate analysis, and the percentage difference. Using exact analysis, the answer we have already computed is 0.4. Using approximate, this is 0.6. So it's not very different. There is only a 2.3% change. It is 12.34 volts for exact analysis, and for approximate analysis, this is 12.03. So the difference is only 2.5%. This means that the results, the bias point computed using approximate analysis is very much like we have computed using exact analysis. There is an approximately 2.4% difference between the two types of analysis. But the approximate analysis, for approximate analysis, we have to do lesser work. This means approximate analysis is a good approximation of exact analysis. In the next lecture, we will study some more biasing techniques. Thank you.